Okay, let's start talking about local averaging. It's a very basic method to create aggregation and segregation. Okay, the tendency for neighbors have similar attributes over time. That's local averaging. Okay, it is called local averaging because it's based on neighbors. Okay, after local averaging, neighbors, they tend to have similar attributes, or just say they have similar states or similar values over time. Repeatedly applying local averaging over each sells more neighborhood, and this is the mathematical function here. Zi is the central pixel, right? T is the current time. T plus 1 is the time after next tick. So Zi T plus 1 means the state of this central pixel or central cell after next tick. It is decided by what? It is decided by the right side of this formula. And there are two terms on the right side of this formula. The first term is ZIT, which means it is the current state or current value of the central cell, but it is multiplied by something called 1 minus W. W is the weight. We call it weight. It varies from 0 to 1. It is called a weight. Later you will know why. But you should know that only 1 minus W of Zi contributes to its next state after the next tick. The rest of the weight, which is, it should not be the rest of the weight. W is the weight. 1 minus W, this proportion of the current value of Zi contributes to the value of Zi after next tick. On the other hand, the second term here means that, okay, we need to calculate the sum of Zj at current time. What is Zj? Zj represents a specific neighbor of Zi. Since we're talking about more neighborhood, there should be 8 neighbors. We calculate the sum of the neighbors. Each neighbor has a specific value, right? We calculate the sum and divide the sum by 8. What does it mean? It means that we need to calculate the average value of the neighbors of Zi, or you can say cell I, and multiply that average value by W. Okay, for example, let's just say W equals to 0.5. What does it mean? It means that after the next tick, the value of central pixel I is decided by two things. One is its current value. Another one is the average value of its neighborhood. But what's the weight? 50% is decided by the average value. 50% is decided by its current value because W is equal to 0.5, right? So now you know why W is called weight. It is the weight for the average value of the neighbors of the central cell. If that's the weight, W is the weight for the average value, then the rest contribution is from its current value. So that's 1 minus W, okay? And that's the reason why W must be somewhere between 0 and 1, because eventually W is actually a percentage. If it is 0.1, it means that 50% of the value of I after next tick is decided by the average of its neighbors. The other 50%, which is 1 minus W, 1 minus 0.5, is decided by its current value. Okay, so that's why it's called local averaging. We are calculating the average value of cell i's neighborhood. And since we're talking about neighborhood, neighborhood is an environment surrounding this specific cell. It's not the whole space, it's a local area. So local and averaging. Local is addressed by the neighborhood. Averaging is actually literally addressed by averaging the values of cell i's neighbors. Okay, so when every cell on the lattice of the on this lattice is following this specific rule to update its state, what's the result? It's always it's a portion of its current value and a portion of the average value of its surrounding. So eventually you will find out that cells, they are getting closer to each other in terms of the value. That's the reason why local averaging refers to the tendency for neighbors have similar attributes or similar values over time. They're becoming more and more similar to its neighbors, because part of it is the average value of its neighbors. If you do this repeatedly, again and again, ticks by ticks, they are going to be similar to its neighbors, and eventually there will be segregation and aggregation. Okay, so here are some questions. I have actually answered them. Why must W fall between 0 and 1? Because it's a weight. It must be a proportion between 0% to 100%. If you choose to assign 0 to W, so here W will be 0. It means that there will be no contribution from its neighbors. On the other hand, the next value of I is simply decided by its current value, which means there will be no change, right? And why 8? Because we're using more neighborhood. There are 8 neighbors. If you are using Van Neumann neighborhood, this 8 should be changed to which value? 4, because in Van Neumann neighborhood, there will be only 4 neighbors. What type of model is this? Phenomenological or mechanistic? Obviously the later one, because this is a mechanism after the updating of cells. Obviously, I have given you, you have created this rule, this mechanism to help these cells update, right? It's not statistical. It's very clear mathematical expression of the mechanism. Okay. And here is the model from the textbook 3.1. I think it's necessary to show you. Let me show you. Yeah, this is a model. This is a model. You can give a weight here, right, from 0.0 to 1.0. And let's just say I gave it a very low value, 0.10 set up. Okay, so this is a randomly created space with different grade scales, right? Let's just do this step by step. So here ticks 0, right? If I click step, ticks 1. Okay, one local averaging has happened, but it's very unclear because it's only one step. Let's just let it go continuously. See that? Okay. Closer cells, they are looking much similar to each other's now. And now simultaneously we can see aggregation here, right here, here, right? If we go continuously, after 144 ticks, we have an aggregation here, another aggregation here. It's not very clear, but if you lean back to your chair and look at this space from far away, you can see here is an aggregation of black, aggregation of white, aggregation of black, right? Here we have a twisted shape here along my cursor. And now we only have a value of W for 0.110, which means that the contribution from the neighborhood is pretty low. It's only 10%. Okay. we used 144 ticks to create this aggregation. Okay, let's change this to 0.6. Here is my question. If I set up and go again, do you think it will take less ticks or more ticks to create the similar aggregation here? Okay, let's do this. 144 for W equals 0.1. Now I'm going to change to, I have changed W to 0.6, which is pretty high compared to 0.1. What is going to happen? Set up and go. Okay, aggregation has formed. I can let it go further, but now there is aggregation. Here we have the black area, another black area, and a surrounding white area here. Now it only took 32 steps or 32 ticks, 32 generations to achieve the similar aggregation and segregation Y. Remember when W was equal to 0.1, it took 144 steps to finish this process of segregation and aggregation. Because what? Because there is much more influence from each cell's neighborhood when W equals 0.6. Okay, the higher the W, the faster the segregation. Right? The shorter time you will use to make all those cells similar to each other and form aggregation and segregation. Okay, you can play with this model a little bit and you will know what I'm talking about right now. Let's get back to the slides. Okay, so here are three bar charts to address the importance of W. Okay, so what's the meaning of this bar chart? Vertical axis is for ticks or generations or time. So 0, 10 ticks until 50 ticks, right? The vertical one is grid cell values. For example, at 0 tick, the values vary from 0.0. That's the lower Whisker. We call this Whisker, or you can say that's the minimum value for all cells, 0. The maximum value is 1.0. 25 percentile is right here, somewhere above 0.2. This is the median value of all cells in the space. It's somewhere right above 0.5. And this is 75% percentile. It's the same spatial distribution of all cells in terms of values for tick equals 0, right? Okay, if we set W, we gave 0.05 to W, which means that only 5% of a cell's value after next tick is decided by its neighbors. Then that's 10 generation, 20 generation, 30, 40, 50. You can say that, this difference between max value and mean value decreases. At the very beginning, the difference is 1, from 1.0 to 0.0. After 50 generation, this range is from maybe 0.3 to 0.7. Obviously, it gets this difference. Let me, right? You can say this is a process of getting similar to each other. At the very beginning, we have pixels with 1.0 as value, 1.0 as their values, and 0.0. But at the end, the range of values of cells decreased a lot after 50 generations. That's 0.05 for W. But if you change it to 0.1, this process is much faster. Sorry, let me, something wrong with my mouse. erase. This is the first situation. That's the second one. If you change W to 0.5, you can see that. You can see the shape of this funnel. If W is equal to 0.5, all cells, they are getting similar to each other in terms of values very fast in 10 generations. And after 20 generations, there is barely change in terms of the values of all the cells on this lattice. So this is the importance of weight. If the weight is pretty high, very close to 1.0, it means that the influence from each cell's neighbors is heavy. On the other hand, if the value of W is pretty low, 0.05, the influence from its neighbors is pretty light. Okay, so this is local averaging. And here, I actually have shown you using that logo, right? This is the very beginning of the spatial distribution of all those cells with different grayscales. And after generations and generations, eventually, the author of the text using contour lines to make sure that you're clear with all those aggregations. And results of the local averaging process applied to a 50 by 50 grade. 50 by 50 grade of cells, starting from the random initial state showing A, okay? And with the state after 10 generations shown for B, C, D, E, F, okay? A is the initial situation, and after 10 generations, it could be B, could be C, could be D, E, or F. The only difference is that different W values were applied to different simulations. For B, W only equals 0.1, right? For F, it's 0.9. It's very heavy. After 10 generations, if W was 0.1, this is the case. If W was 0.9, this is the case. Okay, if you compare B and F, obviously you can still say differences. You can still say difference among cells here. Some of them, they're pretty dark. Some of them, they're pretty bright. But still, after 10 generations, if you use 0.9 as the value of W, this is the result. If there was no contour lines, you can barely differentiate different pixels or different cells, because they are becoming so similar to each other after only 10 generations because of a pretty high W value, right? These contour lines, they are circling different aggregations, okay? Different cells with similar values, but compared to surrounding cells, they are forming smaller aggregations, smaller clusters. Okay, so we have learned local averaging. Let's make this averaging process more complex. Okay, here introduce a random element to account for stochastic effects or random effects. And here we're using Van Neumann neighborhood, okay, which means there are only 4 neighbors. So you can see the form of this formula is very similar to this one, right? To this one. But the difference is that, firstly, here, the denominator is 5 instead of 4. Why? Because here, in this huge bracket, the cell itself is also included. So it has 4 neighbors, Zj, and itself. So all their values, they are summed. Surrounding neighbors' values and the value of itself at t, add them up, calculate average value. That's the reason why the denominator is 5 instead of 4, right? And This part is easy to understand. And there is a next term here. That is what? That is the noise. Noise is something random here. So this epsilon I at a specific time t could be anything, just a random noise. You add it to make influence, to add to affect the value of I after next tick. So this is random. This part is random, right? So you cannot predict it. You cannot predict it. Okay. So local averaging, that's the first term of the right side of this formula, and with noise, that's the second term. Just a random noise. That's it. Okay, here we have different results. Typical outcomes of the VSAC and Sutherland local averaging model with noise, because this model was proposed by these two scientists in 1987. So we just call it V and S model, okay, because their names are pretty hard to pronounce. A local averaging model with noise. These examples were run for 50 iterations on 100 by 100 grid, which wraps both horizontally and vertically. Okay, and the cells with Z greater than the threshold state value ZC shown in each panel are colored gray. Okay, because the existence of this noise is pretty hard, it's almost impossible to predict the value of each cell after next tick, because there is always a randomness here. So eventually, after how many 50 iterations or 50 generations, some cells, they have pretty high value, some of them have pretty low value because of this noise, right? Because it's totally random. We need to use some specific threshold to find out aggregation and segregation, because there are just so many extreme values. If they say is equal to 1.0, it means that all cells with a value equals or larger than 1.0 will be painted gray. So this is the result. You can say most cells, they have a value equals or larger than 1.0. All those white cells, they are below the threshold. They're below this ZC value. So they are still white. So you can say here, we have aggregations. We have aggregations of cells with small values smaller than 1.0, right? And when you change the threshold to 2.0, obviously, not so many cells can be painted gray because the threshold is higher right now. Now we can still say aggregation, but this time aggregation of gray cells, right? We have, you can say tribes, clusters, communities of gray cells, right? And they are separated by, we cannot say linear, but convoluted shapes of white cells. Okay, they are separated by white cells. And if you change ZC to 3.0, which means that even less cells can be painted gray, because you have to have a value larger than 3.0 or equal to it to be painted gray. So this time, gray cells, they are minority. They are minority. So we have small clusters of gray cells across the space, just like we have small clusters of white cells across the space when the threshold value was only 1.0. Now it's 3.0, so not so many cells can be painted gray because the threshold is high. Okay, so this model is very easy, but can be very powerful. It can be used to what? The paper itself, the original paper, the original model proposed by V and S, this model was proposed to simulate the formation of galaxy you can consider each cell as a star, or even each cell is a small galaxy of a larger galaxy within a larger galaxy. It's large enough, right? That scale is universe scale. But Batty in 2005 in his paper, he also used a similar model to simulate what? Urban development. If you compare urban development and galaxy formation, it's uncomparable, right? In terms of scales. But why is this model so universal? You can use it to simulate urban development, and you can use it to simulate galaxy formation, because the background mechanism of galaxy formation or urban development is the same, is the aggregation and segregation of something. Embodies aggregation and diffusion, or diffusion is another word for segregation. These together drive many growth processes, the growth of cities, the growth of the universe. Okay, so you can say that the power of building blocks. This this model, this local averaging model without noise and with noise, right? They're pretty simple. They do not have any context. It's only cells. You can define cells as anything you want. There is no concept, but they're powerful. They are building blocks. These two models, they're building blocks. As long as it fits, you can give a specific context to these models. This context could be galaxy formation, could be urban development. So that's the power of building blocks, basic simulation models. Okay, I will just stop here. Next video, we will start section 3.3 about totalistic automata. Okay, thank you.